Hi there, this is Ayush from Master Mechanical Design and welcome you to second lesson of GD&T Masterclass series. And I have a question for you. Would you tell me which plate of food would you like to eat? On one plate there is yummy tasty junk food and on another plate there is no so tasty but healthy food. You can pause this video and let me know in the comment. But this is not my purpose of asking. What I mean to say is when we were a kid, we always liked to eat junk food 10 times of 10 because it's so tasty. But as our age increases, we becoming more young, we started avoiding junk food and start choosing healthy food. But why? Why? Because healthy food becomes more delicious or junk food becomes less delicious? Of course not. Who does not love pizza? Everyone loves pizza. The fact is, we started choosing healthy food even though healthy food is not so tasty, because with the time we came to understand that junk food is not good for our health. We came to understand the disadvantage of junk food. Excessive consumption of junk food can make us sick or overweight. And this is same with dimensioning and tolerancing method. Direct dimensioning, or we can say traditional coordinate tolerancing method, is just like a junk food, not in sense of taste, but in sense of easiness. Easy for the designers, easy for the manufacturer, or also easy for the inspector. Because there is no such rules and all the controls. But we all know that direct dimensioning method is not good. Whereas GD&T drafting standard is like healthy food. This is only the right method of defining a mechanical design. But it's a mathematical language and having set up rules and control. So it is not so tasty, means it is not so easy. So at the starting of our design careers, almost all of us, we avoid GD&T method and prefer direct dimensioning method. Same like a kid avoid healthy food and love junk food. So how we can change this habit? You guessed it right. In the same way as we start avoiding junk food when we come to know that junk food is not good for the health, when we understand the disadvantage of the junk food. So in this video, I'm going to practically show you that how coordinate tolerancing method, direct dimensioning method is not good. We will go through 7 major disadvantage or shortcoming of coordinate tolerancing method and how the GD&T is the solution for all the shortcoming. And this will also make you absolutely clear that why we need GD&T, why we should make manufacturing drawings only in GD&T standard. Because I truly believe that we cannot master a skill if we don't know that why we are mastering that skill. What will be the outcome of that skill after mastering it? So here I want to start with a disclaimer. After watching this video, 2 things are likely to happen with you. Number 1, you will fall in GD&T, which is a good thing. But number 2, you will lose all the faith in traditional coordinate dimensioning method. So watch this video on your own risk so you don't blame me later. The first and most obvious problem that most of us knows with traditional dimensioning method is we cannot explicitly define and control the form of geometry. We can only define and control the size of geometries. Let's understand it with an example. So let's say we have this tool, a pressing tool, and the height of tool is 65 mm. And let's say our requirements are, first, the tool height should be within 0.2 mm. And second is the flatness of this tool bottom surface should be within 50 micron, which means 0.05 mm. So with coordinate dimensioning, we can define the size 65 mm And we can also control the allowable variation of 0.2 mm by defining this symmetrical tolerance, plus minus 0.1. But we cannot define and control the flatness form 0.05 mm of this bottom surface. The flatness of 0.05 mm of this bottom surface means this bottom surface irregularities, all the waviness, all the up and downs of this whole surface should be within 0.05 mm thickness of rectangular prism, the flatness tolerance zone. And this flatness tolerance zone is independent of the size tolerance of this tool, the height of this tool. And there is no way to define and control this bottom surface flatness independently with coordinate tolerancing method. So to define this, we will have to use GD&T, the flatness control frame, something like this. But I have seen that as a beginner, many of us try to control this flatness with size tolerance, something like this. We associate the flatness tolerance with the size. But this is not appropriate method because first of all, this tolerance is controlling this overall size of this tool too precisely, which is not actually required. For this example, allowable size tolerance is 0.2 mm. So this tighter tolerance is nothing but just increasing the manufacturing cost. Plus, this is not clear that which surface to be flat, this bottom surface or this top surface. So the manufacturer will have to maintain the flatness of these both surfaces with each other. Again, manufacturing cost will be increased. But with GD&T, we can clearly notify that only this surface is required to be flat, independent of size tolerance as well as independent of this top surface. Something like this. 0.2 mm controlling only the size, height of this tool, and 0.05 mm is controlling only the flatness of this bottom surface, regardless of the top surface and the size of this tool. And in the same way, we can define and control the other forms of the geometry as well, like straightness or circularity or cylindricity. The next limitation of coordinate tolerancing is we cannot control the profile of a joint continuous feature as a whole. With coordinate tolerancing, we can only control the profile of individual features. What I mean to say? So let's say this is a sheet metal bending tool, a punching tool, and this bottom surface has a kind of curved profile to bend this sheet in some fancy profile shape. And our functional requirement is this profile shape should be within plus minus 0.1 mm. So in coordinate tolerancing, we can define plus minus 0.1 mm to all radii, something like this. Radii means plural of radius. But here we have to also define the location of these radii with appropriate tolerance. And here I am not sure that how much tolerance we should specify over these locational dimensions to get this profile size within tolerance 0.1 mm. But that's the different problem. Here I want your attention to these radii tolerance. So this 15 mm can be 15 minus 0.1 mm, means 14.9 mm. And these 20 mm can be 20 plus 0.1, means 20.1 mm. So these profile can be manufactured something like this, which we definitely don't want. And sadly, we cannot do anything about it. With coordinate tolerancing, we cannot define and control these all radii as a whole continuous feature. But in GD&T, we can define and control this complete continuous profile as a one whole profile. using profile control frame, something like this, which is not only controlling the size of these radii, but also controls the position of each individual radii to keep these all radii as a one into a profile tolerance zone within 0.1 mm, something like this. Are you feeling the same as I am feeling right now? That GD&T also save the time of the drafting, because here we just have to define the tolerance at one place under this control frame. How simple it is. Next major drawback of traditional coordinate tolerancing method is its rectangular or square tolerance zone. Let's understand it with an example. Let's say we have this metallic component, and this component has a large production rate, let's say 1000 pieces per day. And let's say in this component, the position of this middle hole is very critical. So our requirement is to inspect the position of this hole correctly. So as the production of this component is very high, so we can design a functional gauge to inspect this. And as per the drawing of component, the position of this hole is 25 plus minus 1.5 from left side and 25 plus minus 1.5 from the bottom. And the hole size is 10 plus minus 1 mm. So we can design a functional gauge something like this. These are the side references to locate this part at its sides, and this is the pin to check the position and size of this hole of this component. So if the size and position of this hole will be within tolerance limit, it should go through this pin. If not, then part will be considered as rejected. And this is the basic function of a GO gauge. So now I want your closer attention to what should be the size of this GO gauge pin. So as the component hole size is 10 plus minus 1, means this hole can vary from 9 to 11 mm. So for the GO gauge, the pin nominal size should be maximum 9 mm. But as this component hole position can also deviate from its initial position by plus minus 1.5 horizontally as well as vertically, so we will have to minus the size of pin by 1.5 mm from all sides, means minus 3 mm in diameter of the pin. So the pin nominal size should be 6 mm, 25 and 25 from sides and bottom with gauge tolerances. But here I don't want to go in gauge tolerance calculations. We will learn the gauge tolerance calculation in separate video. So for this moment, just consider this gauge dimensions are exactly 25 and 25. And this pin diameter is exactly 6 mm. And now let's try to check the function of this gauge. So I will deviate the hole size and its position within its tolerance limit. And after the deviation, we will check whether this hole is going through this pin or not. So I'm first deviating the hole size. So it's 10 plus minus 1. So we can go for the lower side, 10 minus 1. Because as this is a GO gauge, so if the smallest size will be passed through this gauge pin, means any size bigger than the smallest hole will be definitely pass. So the smallest hole size will be 9 mm. And this is perfectly passing through. And also with position deviation from left side, we can go for 25 plus 1.5 means 26.5 mm. And it's perfectly fine. Pin will still goes through the hole. If we go for 25 minus 1.5 means 23.5 mm, it will be also fine. And from bottom also, if we will go for 23.5 or 26.5, it will be fit. So we can consider this GO gauge is okay and accepting all the worst condition. But it is not. Why? Because this hole can deviate 26.5 mm horizontally, and in the same component 26.5 mm vertically too. And if this will be happen, this hole will be not go through. And this is how we do the mistakes in coordinate tolerancing method. Because the actual tolerance zone is circular in this case of pin and hole. But the position tolerance zone of this hole is a square because of coordinate tolerance in x and y direction. So at 90 degrees, the radius of circular tolerance zone is equal to the length from a square center to the side, means 1.5 mm, half of the side. But at 45 degree, this become the half of its diagonal length, 4.24 of the square, means half is 2.12 mm. So it won't fit. But with GD&T, we can define and control the position of this hole within a cylindrical tolerance zone, something like this. This diameter symbol represents a cylindrical zone, the fully utilization of available tolerance zone around the pin. And this is one of the most important advantage of the GD&T, because in most of assembly conditions, we always use pins, double pins, or bolt with clearance hole or the threaded hole, and all are the circular. So we must define a cylindrical tolerance zone using GD&T position control frame instead of coordinate a square tolerance zone, which is not practical. Otherwise, a OK part can be rejected or NG part can be acceptable. Next problem with coordinate tolerancing is accumulation of tolerances. Accumulation means adding the things one after one. What I mean to say is, let's say we have this plate with 3 holes, and as usual we did a chain dimensioning at distance of 30 mm plus minus 0.1 mm. So these all 3 holes will have a square or rectangle tolerance zone, as we seen in this last example. So if we will closely look at the first hole, this hole has a square position tolerance zone, 0.2 by 0.2 mm. So this hole can be located at 20 plus 0.1, 20.1 from this side. And now if we will look at the second hole, this hole can be located at 20.1 plus 30.1, means 50.2. So this second hole having a rectangular tolerance zone 0.4 by 0.2. And this third hole will be 0.6 by 0.2. And this is the disadvantage of coordinate tolerancing. The tolerance adding up automatically and increases after each chain dimension. But we can fix it with GD&T. Something like this with position control frame. Each hole is controlled within 0.2 mm cylindrical tolerance zone. And these cylindrical tolerance zone axes are at absolute distance at 0 tolerance from its datum. Means these basic chain dimension tolerance cannot add up because these tolerance do not have any tolerance, and we represent this as a basic dimension under a square bracket. Tolerance is only within this control frame. I hope you are enjoying this video so far, so please give us a like. And the next disadvantage of coordinate tolerancing method is the fixed tolerance zone. And let's understand it with an example. Let's say this is an assembly of 2 parts. One part has a hole and one part has a pin. This hole size is 10 mm at 25 and 25 from the sides, And for this moment, let's consider this female part has no tolerance. It's perfect. And on this male part, the pin size is 9 plus minus 0.5. And the position is 25 plus minus 0.25. Means this pin has a square position tolerance zone of 0.5 by 0.5 regardless of the pin size. Means if the pin will be at nominal size 9 mm, this position tolerance will be same plus minus 0.25 and the pin will be inserted and assembled. If the pin will be at MMC means 9.5 mm, this position tolerance will be remain same and pin will be inserted. And now if the pin will be at its LMC means 8.5 mm, this pin position tolerance will be still the same 0.25 mm. However, if we deviate this pin position, let's say by 0.5 mm, this pin will insert it. Even if we deviate by 0.75, this pin will still insert it. Means this pin is functionally okay. Even if the position tolerance is plus minus 0.75 mm. But as per the drawing, this pin position should be always within plus minus 0.25. Means this part will be rejected in inspection. Even if the part can fulfill the requirement, a good part is being rejected. But we can save this part with GD&T. Something like this, we can define the tolerance zone at MMC. And this indicates that this position tolerance zone 0.25 will be applied only if the pin size is at MMC. Means at 9.5 mm. And as this pin size will get smaller, this position tolerance will be increased in the same amount the pin size will decrease. And we call it bonus tolerance. So after manufacturing of this part, if the pin size is measured 9.5 mm, means pin is manufactured at its MMC, the position tolerance will be considered as 0.5 mm. If the pin size is measured at 9, means 0.5 smaller than MMC, then the position tolerance will be considered as 0.5 plus 0.5. 0.5 is the bonus tolerance and this will become 1 mm. And if the pin is manufactured at 8.5 mm, means the pin is manufactured at its LMC, then the position tolerance will be considered as 0.5 plus 1. Here 1 is the maximum bonus tolerance, means 1.5 mm diameter cylindrical tolerance zone. To check this, we can push this pin at edge of 1.5 mm diameter zone. Means 25 plus radius of diameter 1.5, 0.75. Pin is still inserting. And this is how we can say, first, GD&T gives extra tolerance as compared to traditional coordinate tolerancing. Second, GD&T can reject only non-functional part and can pass all the functional part. Third, GD&T is a mathematical language. As we see that how we calculate the bonus tolerances, this is a mathematical expression. Next major problem with coordinate tolerancing is undefined measuring setup. Let's understand it with an example. Let's say this is a motor and this is mounting plate of this motor, and our requirement is precisely maintain this motor shaft axis from its base, let's say within 0.1 mm. So how we can define this with coordinate tolerancing? So it's very simple. We can simply control the motor position mounting hole from its base within plus minus 0.05 mm. Something like this, 75 plus minus 0.05 mm. Because the total allowable deviation is 0.1 mm, so symmetrically it will be half. And here we do not need to define the tolerance on rest of dimensions of this mounting plate, like the plate length and the width. A general tolerance will be applied because these are not functionally important dimensions. So what manufacturer will do, they will first prepare this plate size and then they will take the reference from its base surface and will make this hole at 75 plus minus 0.05. And now after manufacturing, if inspector means the quality engineer set up this part something like this. First they rest the part over the inspection table surface and then they touch this right angle from the side and then they measure. Then the measurement will be within 75 plus minus 0.5 because this is how the manufacturer took the reference for making this hole during the manufacturing. So this part will be considered as correct. But if the inspector will first align this same part with the right angle and then they rest over this surface plate, then the position of this hole from the base will be something else and probably will not within 75 plus minus 0.05 because here we can see this gap because we haven't controlled the right angle of this corner because that was not functional. And so the same part will be considered as rejected. And this is why the measuring setup, the measuring sequence is very important. A same part can be acceptable or it can be rejected if the order of measurement is different. And we can fix it with GD&T. In GD&T method, we can define the measuring setup as well as the order of measurement with datum, something like this. So this is clearly indicating that the mounting base is the primary datum A, and then B and then C. Because the base of this mounting part is functional. This measurement should be from the base. So the position of this hole with respect to datum A and then B and then C is in order. So the inspector will first rest this part over the datum A and then they will fix the part with B and then C. So a good part will always pass the inspection and a bad part will always reject it in inspection. And this leads us to next problem of coordinate tolerancing method. Unclarity of measuring surface. Means here we are not clear that how the part should be measured. One can be from the datum planes. Like here first we can rest this part over this surface plane and the surface plane is the datum. So we can measure it from the datum. Or the second can be the local measurement. Means we can measure from any point of this surface. Something like this with vernier clipper maybe. So this measurement value will be different from measurement from our datum, from a reference. And we cannot say that how measurement should be like this or like this because there is no such written standard in coordinate tolerancing method. There is no such defined rules that how the part should be inspected. The local inspection is correct or it should be always from our datum. Unlike the GD&T, GD&T has own standard, own written standard like in ASME and ISO. So in GD&T standard, we can clearly specify the datums and all the measurements should be from the datums if datum is specified. So as we have seen in coordinate tolerancing method, you will be always in confusion. Even if manufacturer will manufacture the part as per the drawing, as per your defined tolerance limit, and also pass the inspection, but still there will be a chance that part will be not assembled, or perhaps the part will be not function properly as it's supposed to be. Coordinate tolerancing method has been absolute 150 year way before because of these all problems. But we are still using coordinate tolerancing method. But it is fair to use the coordinate tolerancing method where the part is not functional, like to defining the raw material size. But whenever the two parts are meeting, assembling together, GD&T is only the way to define the part for manufacturing. GD&T is not kind of advanced or latest version of drafting standard. Actually, this is only and only the drafting standard for mechanical design. So as you have also seen that GD&T has many rules. It's a mathematical language. So to understand the GD&T, first we have to understand some vocabulary of GD&T, the basic wording of the GD&T. Like what is the feature? What is the size of feature? Regardless of size of feature. MMC, LMC, mating envelope, tolerance zone, and some more. So let's understand the vocabulary of GD&T in next video. Next video should be on your screen or you can check the description. And thank you so much for your appreciation on the last video of GD&T. Thank you so much.